Hey Black Hat, it's great to be here with all of you. I hope you're having a wonderful time. I'm going to tell you about Surfactant, a tool we developed which provides a modular framework for extracting information from files, analyzing the information, and then outputting the results in a human or machine readable form, typically as an SBOM or software bill of materials. Surfactant is open source, so after this talk, I'd like to invite you to check out the GitHub and star or share it. Before we get into technical details, allow me to introduce myself. My name is Ryan Mast, and I'm a cybersecurity software engineer at Lawrence Livermore National Laboratory, where I work on a variety of projects involving software development and vulnerability research that are aimed at improving the resilience and security of the electricity grid. Surfactant was developed as part of one of these projects, Citrix, which was sponsored by the Department of Energy's Office of Cybersecurity, Energy Security, and Emergency Response. If you want to reach me for questions or anything after this talk, you can contact me on social media at rmast, on GitHub, or by email at mast9@llnl.gov. Now, let's dive in and start by answering a question that some of you may have had to get us on the same page. What is an SBOM, or software bill of materials? In short, an SBOM is like a nutrition facts label with details on what makes up a piece of software. For individual files, it will have basic information like the file size, type, and hashes. It may also contain a product name, vendor, and version information. At a more detailed level, it may try to capture information on what statically linked or header-only libraries make up a binary, as well as capture dependencies on other files or packages on a system in order to establish relationships between them. From a practical standpoint, the information captured will depend on who created the SBOM and its intended use. Generally, there are two levels of detail that a user might care about in an SBOM. There are file-level SBOMs where you try to capture information about every single file in a system and the relationships between files. For example, an executable using a shared library. This kind of detail could be useful for someone doing security analysis or incident response who is trying to determine if a vulnerability actually applies to a system. On the other hand, if the SBOM is generated without access to source code or package manager metadata, then you might not know what a file is. For example, this type of SBOM might not tell you that a file is part of a well-known package such as OpenSSL. It might not even tell you that a file contains compiled code, or if it's just an arbitrary data file. There are also package-level SBOMs that try to capture what packages and versions are present on a system. This can be useful for consumers to get an idea of the risk in buying a new product, or if a CV may affect them. Vendors may use this type of SBOM for tracking what components they need to update. The biggest downside with the SBOMs we've received from vendors that were generated from source code or package manager data is that they do not show how the packages relate to one another, and they don't have information on the actual files on a device. If you ask for an SBOM, you'll probably get a JSON file that meets one of two main specifications. SPDX is an older format from the Linux Foundation that was aimed at license compliance. The other format, CycloneDX, is from OWASP and is a newer format that came out in 2017. It is aimed at cyber risk reduction and supports extensions that can be useful for conveying security-related information to a consumer. Now that we're on the same page with what an SBOM is, let's talk about the challenges that led to developing Surfactant. First, it's important to note that while we work with vendors who send us software, they send us compiled binaries. This means that we cannot use SBOM tools that depend on having access to source code. In addition, we receive binaries for a variety of operating systems. The support software is usually Windows PE files that target the .NET runtime environment. The software running on an actual device is structured firmware that usually runs on embedded Linux or VxWorks, and consists of a file system that often has many files, but limited to no package manager information. This lack of package manager metadata files means that open source tools which try to generate package-level SBOMs will not be able to do very much. Commercial tools do a bit better since their developers usually maintain a database of common or well-known library signatures. However, when we encounter custom file formats, we can't easily add support to a commercial tool ourselves. We have to ask the vendor to add support for us, and while vendors are willing to add support usually, there may be restrictions that do not allow us to share a sample with that vendor. In addition, the SBOM's output from both commercial and open source tools tend to basically just be a list of the files or packages identified by that tool, with no real structure. As an example, here's a graph of an SBOM that was generated from a zip file that contained Windows, Linux, and macOS versions of a piece of software. As you can see, it captured information on individual binaries, as well as some packages like libzerumq and boost. However, you'll notice that the only relationship for all of these is to the root node, that is, the top-level zip file. This is essentially telling us that everything is contained within that zip file, which doesn't give us any interesting information. It doesn't tell us anything about how the different binaries use shared libraries, nor does it tell us where packages were found. For example, we can't tell if boost was found in its own standalone shared library, or if it was detected as a statically linked component within one of the other binaries. The inspiration that led to creating the first version of Surfactant was that if you right-click on a file in Windows, select Properties, and then Details, you can get a bunch of interesting metadata like the product name, product version, and a copyright string that often identifies who made a piece of software. Similarly, on macOS you can select Get Info on a file and see some version information and a copyright string. So, why not leverage all the interesting metadata that different file formats have to create an initial SBOM, then use manual analysis and other tools to add package-level data and statically linked library information to the SBOM. With that background information, let's take a deeper look at what Surfactant is and what we mean when we say that it is a modular framework. To start off, you give Surfactant either a directory or, more commonly, a configuration file that can list multiple directories, alongside supplemental information you provide that helps it establish accurate relationships later on. From there, Surfactant traverses the provided directories and tries to identify the type of each file. For recognized file types, it then tries to pull out additional information from the file that can help with identifying the package the file belongs to, relationships with other files, and information that can be useful for determining what vulnerabilities might apply to the system in the future. After finishing gathering information, Surfactant moves on to an analysis stage that is used to establish relationships between files based on the gathered data. One key aspect of this is that we try to avoid making inaccurate guesses that would introduce wrong information into the SBOM. As an example, let's say I have an application that uses dependency A. The naive approach to establishing a relationship would be to just look for a file with a name that matches dependency A. The problem is, if you have multiple files with the same name that are used by different applications, you have no idea if you create a relationship to the right dependency A file. Our solution to this problem is to emulate how the operating system or runtime environment would find the file to load for a dependency. Let's say this example is using .NET. We internally construct a list of probing directories like the .NET runtime environment would, and then limit our search for dependency A to those identified probing directories. Finally, we write the information out to a file. By default, this is a custom format that includes all of the information we have. However, we also support outputting a more limited subset of information to CSV, SPDX, and CycloneDX files. Eventually, we plan on leveraging CycloneDX extensions to output all information to that format. However, this feature is a work in progress. Now, as for the modular aspects of Surfactant, all core functionality is implemented using the same set of hooks that is available to third-party plugins. This includes identifying file types, extracting information from files, analyzing gather data, and writing output files. Adding features should not require modifying the Surfactant source code. As an example of what is possible, here are some plugins that have been developed so far. Many of these leverage external tools to gather additional information on files. Several recent plugins that I'd like to highlight have been focused on augmenting SBOMs with known CV information by making use of tools such as Intel CV bintool for scanning files, as well as Ankor's Grype and Docker Scout for scanning saved Docker images. Another example is this plugin that outputs a SourceTrail database file, which allows using SourceTrail to visualize relationships between files. This plugin was inspired by Pira, an awesome tool created by Quarks Lab for visualizing file systems using SourceTrail. Taking visualizations a step further, this image from a paper that our collaborators published shows how a graph-based comparison can be used to highlight similarities and differences between SBOMs. If SBOM analysis and visualization is something you want to learn more about, check out their paper. So, enough talking. Let's see what using Surfactant looks like in practice with a demo. To start off, here's a quick look at the GitHub repository. If we scroll down to the README, then you can find some basic installation and usage information for Surfactant. You can also find a link to the documentation, which will take you to the Read the Doc site for more detailed information on the topics covered in the README. Now, open your shell of choice and run pipex install Surfactant. Pipex will take care of creating and activating a virtual environment for Surfactant to avoid dependency conflicts between different Python packages installed on the same system. Of course, you can manage virtual environments yourself if desired. You can also install Surfactant using the GitHub repository URL to get the latest development version, which may have features not yet in the PyPI release. After installation, Surfactant can be run from any directory. Providing the help option or no options will print usage information, which shows the available options and subcommands that Surfactant supports. This demo will focus on the generate subcommand, however you might also find others useful too, such as the merge or the soon-to-be-added config subcommand. If we print out usage information for the generate subcommand, we can see what arguments it expects, a configuration file or input directory, as well as an output SBOM file name. Additionally, you can see some of the options it takes, such as the recorded institution option for specifying what organization created the SBOM. Alternatively, the config subcommand will be another way to set this option in the near future. Another option that you might find useful is the list output formats option for showing what the available output formats are. Now let's download a sample file to try running Surfactant on. For this demo, we'll use precompiled Linux binaries from another open source project, Helix. After the download finishes, we can unpack the archive by simply running the tar command on it. Often, unpacking will be a more involved process that requires using tools such as unblob or binwalk to extract individual files. For Windows installers, we found that running the installer inside a VM with sysinternal's process monitor is a good way to find all of the files installed and their install paths. In addition to the Linux sample, let's also grab a copy of jQuery to use as an example of a JavaScript file, and save it to a subfolder called jQuery. While we could now just give Surfactant the directory these files are in, this is not enough information to create accurate relationships in the SBOM. For that, we need to create a JSON configuration file for the specimens with some extra details to help Surfactant out. The structure of this file is a list of JSON objects, each of which must have an extract paths key. The value for this field is a list of directories that Surfactant should traverse and gather file information from. The paths themselves can be relative to the directory Surfactant is being run from, or they can be absolute paths. In addition, you can provide an archive key that is a path to an archive or installer file that the contents in the extract paths came from. This key will make Surfactant create a software entry in the SBOM for the file specified, as well as contains relationships between the software entry for the archive and all of the files that are found in the extract paths for that archive. Finally, you can provide an install prefix key, which tells Surfactant that the files under the extract path would normally be installed under a particular directory on an actual system. So specifying / as the install prefix would mean the files go under the root directory of the file system, whereas /user would indicate that the files in the extract paths would be installed under the /user directory on the system. Let's also add an entry for the jQuery file we downloaded, and say that it is located under a folder called /webroot. We can now save this configuration file and then run the Surfactant generate command, giving as a first argument this config file, and the name of the output SBOM as the second argument. If everything is okay, you will see output messages like those shown here. Now let's take a look at the contents of this SBOM. Since we didn't specify a format, the custom Citrix format is used. First, you'll notice that there's systems and hardware entries that are empty. Then the software section is a list of entries for the binary files that Surfactant recognized. Each of these entries has a bunch of information, including a unique ID for that entry. For the first entry, we can see that the file name corresponds to the archive that we gave Surfactant. Then the install path and container paths are empty because the archive isn't within another archive, and it doesn't get installed on the system. A bit farther down, we can see that there's a metadata section that says Surfactant created the software entry, and that the recorded institution is LNL in this case. If we go to the next entry in the SBOM, you'll see that it is one of the files from within the archive, lib0mq. As mentioned, the install prefix we provide makes it look like the install path is under the /user directory, and the container path makes it look like the file is contained in the UUID for the parent archive within some kind of internal directory structure. Continuing on down, we can see the metadata section here has a bunch of information that is used for establishing relationships, as well as stuff that might be interesting to an analyst comparing SBOMs or looking at the SBOM to get some sense of what's on a system. It also keeps track of which of the names of files and install paths were actually symlinks. Now, let's go to the relationships section of the SBOM. This section is a list of a bunch of objects, which basically say how software X relates to software Y. You'll notice that for these contains relationships, the XUID is for the archive file, and then the YUID is for software entries that correspond to individual files extracted from the archive. Using this first entry as an example, the relationship is saying that the Helix tar file contains this YUID, which, if we jump up, corresponds to lib0mq.so. Jumping back down, we can see that lib0mq also appears as the YUID for uses relationships. Scrolling up, we can see quite a few instances of it being used by other software entries, and scrolling back down, we can see even more entries that use lib0mq. If we go to one of the uses relationships, we can look up the XUID and see that it corresponds to Helix recorder, and the YUID corresponds to lib0mq.so. So this tells us that Helix recorder uses lib0mq.so, and from the number of other relationships to the same YUID, so do quite a few other files. Alright, remember how I grabbed a JavaScript file earlier? Let's go over to the software entry for jQuery. Here, we can see that the install path makes it look like it was installed under /webroot. Also, going down to the metadata section, we can see that there is a JS libraries entry that has the name of the JavaScript library, in addition to identifying the specific version of jQuery. This feature is powered by the database of patterns that retired.js has for recognizing common JavaScript libraries. Let's shift gears a bit and look at installing plugins. For this example, we'll use the Grype plugin to get CVE information for an Alpine 3.16 Docker image. After saving the sample image into its own folder, we'll open our specimen config file again. Then, we can add a new entry to the file with the extract path for the folder containing the saved Docker image tarball. Since we used pipex to install Surfactant, we will use pipex inject Surfactant to install the plugin into the same pipex managed virtual environment as Surfactant, and to then install the Grype plugin from a subdirectory in a Git repository. Once the plugin is installed, Surfactant will automatically detect and activate it. That means we can simply rerun Surfactant generate to create a new SBOM that includes information gathered by the newly installed plugin. If we open up the new SBOM and go to the entry for the Alpine Docker image tarball, we can see that the metadata section of the SBOM now has a list of the vulnerable packages in the Docker container that were detected by Grype. To wrap up the demo, let's take a look at how you write a plugin. We'll use the fuzzy hashes plugin as an example. In the GitHub repository, let's go over to that folder, and you can see that it's basically just a pyproject.toml file and a Python file, making it a valid pip installable wheel. If we open up the pyproject.toml file, it's just the typical metadata you usually see in a Python package, along with information on the dependencies that need to be installed. One of the key details is that it should have a Surfactant entry point, which is what enables Surfactant to automatically discover the plugin. If we then jump over to the Python file, you can see that it's a relatively simple implementation as well. The key details are that it imports Surfactant plugin, and then implements a function that has the Surfactant plugin hook impl decorator applied to it in order to expose a hook that Surfactant will recognize. Currently, the most up-to-date source of hooks that can be used is in the hookspecs.py file, which has a number of function signatures decorated with the hookspecs decorator. These include identify file type, extract file info, establish relationships, write SBOM, and read SBOM hooks, as well as a short name hook that can be used to give an alias name for referencing a plugin that implements one or more of the other hook types. Alright, so by now you've heard quite a bit of what Surfactant can do, as well as seen it in action. Here's a snapshot of what's next. First, we're always interested in handling new file types. In particular, being able to gather more detailed information on scripts written in languages such as Python is an area we're looking at improving. Beyond that, we We are also looking at ways to gather package-level information by leveraging existing tools and exploring techniques to identify packages even in the absence of metadata files from a package manager. However, we don't just want to list identified packages, we also want to make sure it's possible to dive in and see the files that make up a package. Next, we'd like to add more output formats that will be useful for an analyst to visualize the contents of a system. Finally, we have lots of ideas for plugins that we would like to implement, and we want to keep adding features that will empower third-party plugin developers to implement their ideas. As some next steps, you can find additional information on the GitHub repository, so go check it out, read the docs, and share or star it. We'd also like to invite you to try out Surfactant and play around with it. If you find any bugs or have feedback, please open an issue or start a GitHub discussion. Pull requests with changes are welcome, and if you develop a new plugin, we would love to hear about it. Also, feel free to reach out on social media or via email with any questions or ideas you have. And finally, thank you for being here. I hope that you enjoyed learning about Surfactant and that you have a wonderful time at Black Hat.